In reading wiring diagrams, it is important to know that a further development of the actual relay is the transistor, which is simply the same version, only it is controlled electronically without any moving parts. Transistors are divided into emitter, base, and collector. Those three leads are actually interconnected within the circuit, usually inside a computer or module, and it is actually how the different loads are actually tested. By applying a small pulse at the base, you actually complete the circuit between emitter and collector, and this is how transistors actually trigger the load. There are two basic type of transistors, the NPN and the PNP, and this simply has to do with the material of which it is made internally. This has no effect whatsoever on your diagnostics, but it is always important to know because this is how they are connected to the circuit. Transistors, again, are solid state devices which have no moving parts, and they actually trigger a load on and off, much like a relay does. The difference between a transistor is that they can be pulsed, as opposed to a relay which will not take a pulse. Relays are devices that if they are pulsed, the actually pulse rate or the frequency has to be very low, because they will simply not function that way. Transistors can actually be pulsed, and this is the reason why they are widely used throughout automotive systems. They can simply be pulsated, as we see in this schematic, and a small pulse at the base actually triggers a high current change at the output, therefore controlling the load. So again, pulse control transistors are the basis for duty cycle control devices. And here we see how the actual transistor becomes an actual circuit, on and off circuit, which can be pulsed. Remember, you cannot duty cycle control a component using a relay, unless you actually use the relay to provide the voltage source. You have to use a transistor to actually pulsate a device. Most transistors made out of silicone will drop 0.6 volts between base and emitter leads. If it's a zirconia based transistor, it will drop 300 millivolts. This is important whenever trying to test transistors within a circuit, but again, most of these transistors are found inside ECM. It is simply important to understand how these components work. The biggest transistor that you will ever see within a vehicle is actually the ignition module, or the igniter. Igniters cannot be tested as you would in a regular transistor, because most of the time they are connected into a Darlington pair, which are actually two or more transistors interconnected amongst themselves to create the high current needed to drive those circuits. Switches are manual devices which are actually used to turn on a load from a remote position. By understanding the current characteristics through a switch, you can later actually understand the current flow through a relay, and even better, a transistor or an actual solid state relay. By simply connecting a clamp-on current probe, you can actually ascertain the actual flow of current throughout that contact switch. If you want to know if the right amount of current is flowing through that switch, simply look at its fuse. Remember that fuses are always rated at twice the current capacity of that circuit, so that a motor that's connected to a 20 amp fuse will always draw a nominal amperage or current of 10 amps. The doubling of the amperage rating on the fuse is due to prevent unnecessary popping of the fuse due to a surge within the circuit. The voltage drop across a switch is also extremely important, and by simply measuring across the actual switch, we can actually ascertain whether we have a problem with that switch. A switch is a straight through connector and should drop no voltage. Again, if their contacts are actually sulfated, you will have excessive voltage across that switch. For the most part, switches will drop very little voltage within the 10 or 20 millivolt range, and this is at its maximum. For the most part, any switch or relay, for that matter, will actually drop very, very little voltage. Relays are actual mechanical switches that are triggered by a magnetic field within an actual coil inside the actual relay itself. Within a relay itself, the actual toggling of the switch is not going to be done manually. Rather, it's going to be activated by the actual magnetic field inside the actual coil. It is for this reason that whenever testing relay systems, always make sure that there is actual current flow across the coil terminals. Here we see how on a Bosch type relay, the actual magnetic coil terminals are denoted by terminals 85 and 86. Again, this is changes depending on the manufacturer, but for the most part, just simply remember that there has to be current flowing through the relay coil in order for that relay to be energized. The actual contacts are measured or tested in exactly the same way as you would on a regular contact switch. In other words, there has to be no voltage present between the actual contact points of the relay. Here we see that whenever we actually test the operation of a relay, first test the actual output. The output of a relay, which you actually measure between either power or ground. In this case, this relay provides a positive pulse. So you actually measure between ground and the actual output of the relay. In this case, actual battery voltage should be seen. Secondly, you actually test for actual voltage present across the coil of the actual relay. A pulse or a steady voltage or current should actually be seen across the actual coil, indicating that the relay is actually energized. Once you know that the actual relay is energized, you can then proceed to test the actual contacts of the relay by performing a voltage drop across the actual relay contacts. Before actually proceeding to test the relay contacts, a very good step is to actually determine if you actually have power or voltage source at the actual relay input side of the terminal. Terminal 30 is usually used for voltage or current input, but again, this changes from manufacturer to manufacturer, but it is always important to know and to simply understand that you actually need a voltage or a current source to actually trigger whatever load it is that you're trying to turn on. In this particular case, this relay is actually triggered by the actual ECM, which provides a positive volt or a current source on the positive side, completing the circuit across the coil to the negative side. And this terminal should actually, as we did before, should actually be checked for a voltage source. Again, not all relays are triggered by computers, and a lot of them are triggered by switches and so on and so forth, but you should always make sure that you have a voltage or a current source going into the relay. And again, the final step in relay testing is to simply make sure that no voltage is being dropped across its internal contacts. In other words, the relay acts as a straight-through conductor, and very little voltage, usually at a maximum within a range of 20 to 30 millivolts, if that. For the most part, they're very, very close to zero. Relays could be either positively triggered or negatively triggered. If it is a positively triggered relay, like in a upper example here, the actual switch or ECM, whatever is triggering the relay, actually provides a positive voltage. The other side of the coil is going to be connected to ground, and this is how you determine how the relay is actually triggered, and this is important whenever trying to follow the current path. In the bottom example, we see how a negatively triggered relay, we actually, the ECM or the switch actually provides the negative, and we see how the other side of the coil is directly connected to the voltage source, and the current flows in a different pattern. So whoever provides the actual pulse, whether negative or positive, that's what's going to determine whether the relay is negatively triggered or positively triggered. Again, you can simply go and study your diagram and determine whether the actual coil is directly tied to ground. If it is directly tied to ground, then you know that the actual relay coil is going to be triggered positively. If it is directly tied to positive or voltage source, then it is going to be negatively triggered. Again, this is all very important, since the actual triggering of the relay is going to determine the actual flow of current. Here we see how we can actually test the actual coil windings of a relay by actually measuring the current flow rather than the voltage across the coil. Relays drop very little current within the range of 3 to 500 milliamps. So it depends on the actual relay that you're testing. If it's a big enough relay, you could drop even higher than that. But as a rule, relay coils drop very little current. The other way to actually test the second part of the relay, which are the contacts, is by measuring the current flow across the actual load or the output of the relay. Remember that all you have to do is look at the fuse to which this relay is connected to, and fuses are always rated at twice the current carrying capacity of a circuit. So if you are trying to determine if the say for example a motor that is connected to a relay, in this actual example, you're trying to determine if this motor is drawing the appropriate amount of amperage or current, all you have to do is look at the actual fuse to which this circuit is connected to and divide it in half. If it is a 30 amp fuse, you know that the nominal current carrying capacity of this circuit is going to be 15 amps. So again, always divide the fuse to which the circuit is connected to in half, and that is the nominal current. It doesn't have to be exact, but it will hover around this half figure of the actual fuse.